The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people are evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, the group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everyone, I am geologist Philip Ong, here with Mr. Dane DuPont. We're brought to you guys on behalf of HawaiiTracker.com today, and today is Thursday, July 15th, 2021, and today we have in store for you guys a Kīlauea Maunaloa volcano update. And we will be taking some questions in between our volcano segments, and Dane will be monitoring questions in the chat as well, so you can get them to him that way, and he can answer what he can as well, and let him know if there's any issue with our streams as well. So be checking out our streams as we go along as well. So we're going to start today with Maunaloa. We're going to switch things up a little bit and do a little bit of Maunaloa first, and then we'll take a little break and say some thank yous, and then we'll go into our regular Kīlauea, catch up on the monitoring signals and the patterns that we can see, and then we'll wrap things up at the end with touching on the volcano watch that came out today, which is a 1984 Maunaloa eruption. We're not going to go through the full eruption, but we'll look at some of the curiosities that article brings up, and look at those little nuances as we build towards someday telling that story all the way in full. So starting off here on the screen for you guys is two views of that 1984 Maunaloa eruption. This one on the left is, you can see the summit appear at the top part of the image. See if I can get my drawing tool over here. There it is. That's the summit caldera, and then coming down a northeast rift zone, you see this line of cracks that are steaming and lava coming out down here. This was that first phase within the first 12 or so hours of the eruption when lava was still coming out and actually flowing down towards Kīlauea at this point in time. And this is before the fissures continued going down a rift and eventually popped out, where this photograph picks it up further up here. And let's see if I can get that upper part to show for you guys. Might be difficult, but there it is a little bit there. So that upper fissuring down, further down, and putting out this big, nice lava channel that's braided, splits around some topography there near by the rift zone, and cascades down there. So this is a little teaser for what's coming later in 1984 Maunaloa. Of course, this is not what's happening right now. Right now, the volcanoes are both quiet on their surface, but showing interesting signals underground. So, looking at Maunaloa, we'll look at the earthquakes here that have occurred over the past month. This is what this plot actually shows. And you see there's a little bit of a cluster over here, earthquakes this past month, and you see this more diffuse activity on this upper southeast flank here, and a little bit in the upper southwest rift as well, but really there's not a lot of activity. I can zoom it in a little more for you guys, but there's not a huge amount to see there for the past month. The past month, of course, is a big window of time to catch a lot of events, and we're catching some, but we're not catching those occasional flurries that were really populating these charts when we're looking at this 6 months ago or so. So that's the past month. If we zoom in a past week here, you can see there's even less activity. Still a little bit in that northwest flank area over here. Upper southwest rift, we kind of group that with a summit. Summit, upper elevation flanks is often how this goes, this area up in here. I'll talk about this shortly as well. Still some sporadic activity over here in this upper southeast flank, but really not a whole lot to speak of. This number over here says 52. Here's actually, zoom this in for you guys. These plots have an automatic count here and a title. 52 events on this particular map. That's just one random bucket of a week from whenever I happen to load the map there. So that's the earthquakes, pretty low on the summit. But if you go to the Maunaloa volcano update, put out by the USGS every week, and the weekly update came out today, earlier this morning, Thursday, July 15th. And not a whole lot of information, maybe at first glance here. You don't see a whole lot of change, not erupting. Seismicity remains slightly elevated and above long-term background levels, and otherwise no significant changes from other data streams that would indicate increased volcanic hazard at this time. But it is interesting to look at how they break down here in observations. During the past week, they recorded approximately 42 small magnitude earthquakes beneath the summit upper elevation flanks of Maunaloa, and 106 beneath the volcano's southeast flank. So that's really all that there is new in this information, in this update this week, is just these two numbers, 42 and 106, and of course the lack of anything else that would be noted, such as other swarms or big events or changes in deformation and all that. So none of the other stuff is happening, and really you just have this 42 and 106. And just on its own, it's kind of hard to quantify that, because when we're looking at these maps that are automatically generated by the USGS, this is the area that's the basis for those plots, the automatic plots of earthquake counts that are on the USGS page as well. So that's like this plot right here that looks at earthquake rates over the past year, is looking at that in that smaller geographic area right in there. So this is a pretty good indicator for that summit area, but it's definitely missing that flank activity, right? So we're going to rectify that, because what I've gone through and done is gone and tallied these weekly reports and then the numbers that are given, and produced a plot that looks like this. And let's see, I'm getting a title up there. I think I need to do this. There we go. Okay, so this is based on USGS weekly reports, and what you see here at first glance is the blue bars are more or less what the blue bars are on this other plot that we just looked at from the USGS. The pattern should be roughly the same. Depending on when you cut your buckets, it's slightly different, of course, so I think that there's a little bit of a shift in there based on that. But more or less it's the same. You see a higher peak, lower values, little bumps, higher bumps, and coming down, and that pattern is still evident here in a blue line, right? Similar kind of pattern here in a blue. That's that summit area. What I've also done is I've added on here in yellow. Yellow is the south flank counts by week. So you can see that they kind of come in batches. And also while I'm at it, the red is those usually included in a summit and upper elevation flank counts, but those swarms northwest of the summit that are noteworthy and a little bit separate there. So you can kind of see that there are certain periods of time, like right in here, that was November 11th or so through about December 16th, where we really had a phase of increased flank movement, right? Flank movement to the southeast, but then also swarms to the northwest, probably reflecting some adjustment of pressure under that area as well. And then you see it kind of dies off. You have a little bit of activity, but it really picks back up again in mid-February or so. So mid-February, and then it goes on for a little while until the end of March or so. And then really since then, it's been fairly quiet. And more recently, within the last month, 5 weeks now, we've had reports of significant flank events that are actually more in number than the events that are counted at the summit area up there. So that's interesting. Just another thing to note there, right? So I mean, it's something that's not as obvious and apparent. I thought we'd try to freshen things up a little bit at Maunaloa this week and add this perspective, this dimension. It's hard to really tell how this all goes together. So one other step I've taken here is I've superimposed the GPS plot that's across the summit of Maunaloa from north to south. Right, and I've taken off the scale here, but you see it, these little blue dots are now superimposed on here. I can go follow this pattern like this. Right, that's the extension across the caldera. You can see how it correlates more or less with these periods, right, where you can see where this first era of flank movement was occurring during a similar, not a whole lot of extension or contraction, was fairly flat in GPS around that time, right? And then right afterwards we have larger swarms in the northwest, and then we have an increase that came in over here in this first event, an increase in the GPS and the earthquake counts here. And then afterwards, GPS resumes its extension spreading. And interestingly, while it's still spreading at this part up here, is when we begin to have the second bout of flank movement. And you can see that towards the tail end of that is when our GPS dives back down, and then since then it's when it stayed stabilized. And more or less when that flank period of adjustment ended is when our GPS seems to have stabilized as well. And now our most recent, currently ongoing batch of flank movement on Maunaloa here is showing not a whole lot of contraction or extension on the GPS. Once again, similar to that first batch over there. And we still haven't had these larger northwest of the summit flurries, and so it'll be interesting to see if we have one of those that comes up here as well. There are more events than are marked on here. This is just based off what's mentioned in the USGS weekly reports, and so maybe we'll be able to update this in the future and try to incorporate more of the data across more of the sectors by actually farming our own data for that. So that's the pattern there, and this fits into this paradigm we've been using for a while that is illustrated here by Walter and Ameling from their paper of the volcano earthquake interactions in Maunaloa. And they're putting this forth as it relates to an actual eruption, where we're going to essentially ignore that eruption part of it and just say that there's just dike intrusion or movement of magma underground within the existing reservoirs that are expanding through flank movement there. So essentially what you're having is you have the magma coming into the area. We'll just pick an area to start. Let's just start here. The magma comes in, it's coming in, and so it's pressurizing the area. And the magma can, if there's enough holding it back on the flank that it can't actually just fill that already existing area, then it can actually cause an eruption or cause a larger failure of the flank through a bigger earthquake, so to speak. Right now, it seems like it's moving through smaller adjustments. So we actually have magma filling the reservoir, probably more so in the middle right here, and this up and down part that's right in there, right, filling in there. And then that's leading to more pressure, more so on the south flank. I'm going to call this the south. I'm going to call this the north. The north doesn't move as much, so you're not really getting a whole lot of extra pressure on this side because you have Mauna Kea, Hawaii, all in this direction holding it in, whereas on the other side you have Kīlauea that's free to move towards the ocean. So really, it's this side on the south that's the one that's building pressure. That's when you have, whether it's one big earthquake as proposed in this paper, or a series of small earthquakes, or increased earthquakes under the flank, just as lower level activity, right? As showing that you're not building up that potential energy to actually break it. You're just actually moving it through smaller adjustments, more frequent smaller adjustments, rather than a large, huge adjustment. So we haven't caught yet. We're not to the point where we need to pressurize it to fail it yet, which would seem to indicate that we're not to the point of actually inducing an eruption real soon, right? You'd imagine that you'd expect that these flank events would slow down at some point before that. So we'll of course wait and see what the patterns are, and we don't have to rely on only earthquakes. This integrated approach, of course, looking at the earthquakes, GPS, the tilt, and INSAR, gas emissions, all that stuff all together to essentially monitor the volcano. So, but the earthquakes occur, and that allows more room in the middle, right in there, and that allows more magma to come in and fill. So you have a cycle of filling, and just essentially pushing this flank out of the way as it fills this area. And it's interesting to think about how it's doing that with currently this upper area over here not spreading apart, right? So somehow maybe without putting a whole lot of movement to this upper part of the reservoir, maybe it's moving it more on this side of the reservoir right through here. And so that's actually pushing more here without changing this area, right? So essentially the center of deformation is now moved to somewhere over here because you're leaning to the south there, the flank that's actually moving, and it has always been the one that's moved through all the research through past eruptions. So that's the Maunaloa story there. And we will look at the curiosities from the Volcano Watch here at the end. So if we have any Maunaloa questions, we can break in and take them, Dane.
All right, but before we do that, I do want to thank some of the people that helped make this possible. First and foremost, let's thank our sponsors. We have Kalani Tours. They do tours, personalized tours of the Big Island, focusing on the volcanoes, waterfalls, as well as the Kona coffee. And the idea is to give a little bit more personal experience and a little bit more educational experience to those that are coming to our island, as opposed to the big tour companies that'll kind of just shove everybody on a giant bus and shuttle them around. This is really the type of tour that gets people more interested, more involved, and really understand some of the nuances of Big Island. So we thank them for their support. Also like to thank Kīlauea's Bar and Grill in the heart of Pahoa. Do some unique twists on some local dishes, as well as some more traditional dishes as well. So they do some really good ribeye. Also, their fish and chips is great. They have indoor-outdoor dining. So some COVID-safe policies. Full bar. Really a great spot for locals or visitors to go check out if you're in Pahoa. We're also brought to you by the Hawaii Community Foundation Puna Strong Grant, which helps us to continue this type of content. So we do appreciate all of them. And let's get into some questions now, huh?
Sounds great.
All right, so we only have two I'm seeing right now. If anybody else has one, I'll look in the chat one more time before we finish up. Robert asks, not about Maunaloa, but in general, is the liquid lava the same weight as the lava after it cools?
For the most part, yeah. But the with the caveat that the biggest factor that affects the density of the lava is how much gas is mixed into it, which is sometimes 20%, maybe on average, and it might be a lot more than that, depending on which particular flow and how close to the vent you are. So if it were to break down and powder and crumble down, and you lose some of that pore space, then it might be a little bit different, right? If you have the lava is able to degas in the puddle, for example, and then those bubbles become bigger bubbles that escape or kind of become localized and concentrated, and the rest of it doesn't have bubbles, then that lava might be denser and thus would weigh more per amount. Yeah, so small variations certainly are possible from the gas content, most likely, but without that caveat, then essentially, yeah, it's the same. There's obviously some temperature differences, but pretty dang close.
We have a $50 super chat from Through the Eyes of Lisa Mona. It says, thanks for the update. Appreciate it. Mahalo. We do have a question from Tarzan. He says, we asked, because Maunaloa is decades overdue for the next eruption, will it be more intense because of the years of magma buildup?
All right, that's a loaded question there. So thanks, Dan. We can give something to talk about for a couple minutes here. Well, the first thing is the idea of it being overdue, right? And overdue is just based on some pattern of period that we've averaged out. And so we have all kinds of averages of how long the volcano goes between eruptions. For example, the long-term average ranges from 4 years, 6 years, 7 years between eruptions, depending on what period of time you're using there to average it over, right? That's one way to measure it. Another way would be to look at the more recent eruptions. So between 1984 and 1975, that was 9 years. Between 1975 and 1950, that was 25 years. So those are both significantly above the average. We might have a new average that's going on now. Even that said, this current gap since 1984 is going on is the longest one that's been recorded in a volcano's history. Which is not that long, a couple hundred years, which is really just a sliver of time as far as what the volcano can do. So that's the whole overdue aspect of it, right? So, but that does, how I would make that translate that into science, perhaps, is to think about, okay, well, and to the point of your question, does the magma reservoir in a mountain just keep expanding and expanding and expanding over time as magma comes into it, so that it can all erupt all together the next time all at once, perhaps, right? Might be another way to phrase that. And the data shows really that south flank has been moving much of the time since the early 2000s as magma comes into that deep rift. So what's not clear is how quickly the magma on the edges of that, it's kind of a big planar body, right? A big sheet, think of it that way, right? So it's very skinny and very tall and wide, tall and long, right? But it's very skinny, so it can actually lose heat into the walls much faster from that skinny direction. And it's not quite clear how quickly that's cooling and solidifying in comparison to how quickly the magma is coming in. So if it's cooling exactly the same rate as it's coming in, then you end up with the same size reservoir. If it's coming in slower than it's cooling, you end up with a smaller reservoir, or you could end up with a slightly larger reservoir as well. We think that there's multiple levels of storage within the volcano. There's that deeper one, which is probably controlling all this movement, but there's also a shallower one that's really the one that's likely to fill and pressurize and burst first as that last place it can fill and accommodate itself before it goes, right? So it's a lot of different nuance in there, right? But the point being that it probably will not be bigger the next time because there is a process of cooling that removes magma from the reservoir over time. You likely are to have some eruption that's perhaps, you have a range of, some small amount to the full capacity of that upper chamber. And maybe that upper chamber, one example of that might have been 1950. 1950 is a historical eruption in Maunaloa that put out the most lava in a short time. That maybe gives us a proxy of that was that whole upper chamber emptying all of itself that it can at one time, right? So it gives you some kind of upper limit of how much it would put out. And everything else is happening deeper than that. It's probably adjusting through this process of the flank moving and cooling to the sides and all of that, as far as we can tell, right? So it's always possible that, because really what always breaks Camel's back in these kind of eruptions is, quite often you have some new batch of magma comes in from below through all of this mess. And so it's coming into the system that already has all these different imbalances, and so it's when it comes in, can it send the whole system to the point of strain, right? So we're not seeing that spread in Maunaloa right now, and if we were to see it start spreading really quickly, then you might say, okay, based on that, there's a batch of magma coming in and that could cause a big eruption. And so it's more about that dynamic of how much is coming into the base as well, not just what's storing within the mountain, so to speak. So kind of a long answer, but it gives me a chance to talk about some of the dynamics that didn't get into in today's update before that.
All right. Next question is on Mauna Loa. It's from Bill. He asks, I'm amazed that the Mauna Loa lava flowed to reach the ocean in 3 hours. Why so fast? Other flows took days or weeks to reach the ocean. So talking 1950 lava flow.
Yeah, so the 1950 lava flow is in an area that puts out some of the largest volumes and has some of the steepest slopes and has the shortest distance to the ocean from the eruptive fissures. And so it's the combination of all those things that lead to those really fast to the ocean times, especially in that south to southwest part of the mountain, right? 6 o'clock to 9 o'clock on a direction there that really is the most vulnerable to that. In 1984, since we're talking about that a little bit today, the lava was flowing out of Northeast Rift Zone north into the saddle towards Hilo. And even though the eruption was putting out a lot of lava, it was much flatter ground and a much longer distance away, and the lava flow couldn't sustain that long open channel. In fact, it kept breaking its levees further upslope and diverting itself before it could actually get that close to Hilo. So that's, and of course Hilo's on the ocean, and very few lava flows in Mauna Loa get all the way into Hilo and to the ocean. So that's just another way to talk about how important it is to monitor where the lava is coming out and where it might come out and what response you might have, and have it be tailored accordingly to that slope and also to the eruption rate.
All right. All Boomer asks, I've heard references to pit craters in our streams. So how are they formed?
I wish I had the graphic to pull up right away. But what essentially you have some magma that's in the, we talk about magma moving underground all the time. Well, if it's in some area that's in we'll call it a pocket of magma, and that pocket gets mobilized, let's say that it suddenly is able to flow into the rest of the rift and join the movement to some eruption downhill or something like that, right? That's a likely way that happens. Then that area, that pocket that once had magma and now does not have it, is now has a void space in there, and that void space will start eating upwards at that roof of that area, and that ceiling will start falling in. It'll start essentially material start falling as it kind of opens further and further and further upwards, and eventually that'll reach the surface, and you have essentially a vertical shaft with a pile of rubble at the bottom. And it's over an area that some distance way below that at one point had stored magma that moved away, most likely. Right? You could also have just more area, right? And if the crater is formed, let's say, between two long faults, which is often what can happen, and those faults altogether widen and make more space, right? Then you can have more complexity down below as well. But I'll leave it at that there.
All right. One last question, kind of asking for a summary. Kuto on Facebook asks, so what are the major takeaways from all the Mauna Loa data this week? Does everything seem stable according to current background levels?
Yes, I mean, it's stable. The background is a different kind of background. It's a background of adjustment and movement. And, that plot I showed you guys of the different earthquake rates, so it goes back a whole year, right? So really for much of the last half of the year, this adjustment phase has been ongoing, and so it's just still going, it's still adjusting slowly. And in that sense, I would call it stable, right? It's not stable in the sense that it's unchanging, because it certainly is changing, and it's changing towards an eruption at some point, but that's not indicated at any point, any point real soon. Still, we'd like to talk about it now, because that gives us a basis for when something does happen to talk about it and relate it to what's happening now as well.
All right, well, that'll do it for our first segment of Q&A. We'll do one more at the end, focusing more on Kīlauea. Oh, actually, 1984, I guess, too, will fall into that one.
Yeah.
So, if any questions, leave them in chat.
All right, so let's transition here to our Kīlauea portion of our update. And this is the view of the last 24 hours on Kīlauea, and there's still no glow. There's, it's still very quiet at the surface. That's the visible view there. Here's a thermal view from the F1 camera, and there's still a few hot spots. You see it around the west band in that cooling lava lake surface right in here, and you do see it also along the perimeter of the lava pad there, and over here on the right side a little bit as well. There's a hint that there's more of these areas over here, but the camera angle is probably not right for being so far away. We can take a quick look here. We probably have some steam or something that's causing this psychedelic effect here with a flashing orange and red that normally filter out, but it's not the case with these automatic USGS frames. And so our maximum temperature I'm seeing here might say 200, 220. So it's still in that below liquid lava range. And so cooling areas there.
We're going to need to add a seizure warning.
We'll flip that off there and we'll show you guys what's happening with the crust of the lava lake. And so here's the last month of the depth of the lava lake. And you see there's all this variation that happens every day, and it's not quite clear exactly what that is, whether it's effect on an instrument or if it's actual movement of the crust itself that's doing that. In any case, we can visually average it and maybe take this middle point here as the actual trend. And we can see that we start off at somewhere around 225.85 or so meters, and we end up down here at 225.75 meters. So that's 10 centimeters difference right there. It's about 4 inches, and the trend maybe goes something like this, right? Very slow decrease, 4 inches in the last month, and that's a whole lot less than it was the previous month, right? So the previous month, rewind here and save this one from before, back to where the last time we saw a raising of the surface was on May 13th, so we've now passed 2 months since then. And that put it at a max here of somewhere in a range of 229.3 or so. And really, it was decreasing slowly as well up until June 5th, where it had this big 3-meter, 12-foot drop right in there, that big settling event. And then since then, fast forward it here, since then it was resumed that slow, gradual, with some little wiggles in it, which is interesting, right? So, you know, maybe if I were to drop more carefully, maybe you see it go down, maybe you see it come up a little bit, and maybe it comes down, and, you know, we might discount that at first. But you got to imagine that there's a huge amount of liquid lava under that crust, and it could certainly be shifting around in some small ways as the crust above it settles, especially when you have some areas that are different thicknesses and densities, right? Like that big island that was made of cinder, and the levees and the hardened crust of the lava lake itself. So just an interesting thing to note there, and everything is pretty quiet on the surface there. Last thing that's quiet on the surface we can talk about here is this SO2 measurement. So tons per day. Our earlier range had been in the 50 to 70 range or so. And we had this one measurement that was higher, which is not alarming in itself. It's still within that background range. And then 2 more recently, one on July 6th and one that just came in yesterday, it appears, on the 14th, down here at 60 tons and 70 tons per day. So we're still within that range of, we'll call it 60 to 110 now, over the last month here of SO2. So that's still pretty quiet, still considered background on the surface. And in celebration of that quiet surface here, turn to this picture of the Kauea, the white-tailed tropic bird, which if you go to the national park, something you can be seen to be flying in and out of those craters, maybe not quite all the time, but a lot of the time. So something that's unique there. They like to live in these cliffs or these collapsed craters all across the summit and the rift zones of the volcano. So the Kauea, one of 2 images released this week by the USGS, and that's something that they're enjoying as well as I go down to monitor the volcano and look for any changes there. So turning to the subsurface information here, we'll look at the earthquake rates for the past year to start us off here. And here we are at the right end of this graph. This is earthquakes per week, and you can see that we're at some elevated level. I'm going to have one lower week in here, but our past one put us back up to the range of our previous ones right through here, right? And overall, maybe we're averaging somewhere in here around this 400 earthquakes per week mark, and quite a bit higher than during the eruption when it was lower down here. And we're comparable to what we're seeing as a baseline back in the latter half of last year. I call it the baseline because we also had this Kauiki swarm superimpose, and we also had intrusion and a buildup to 2020 right through here. So we're looking for this kind of activity, and just because you see it doesn't mean eruption is coming, as was the case back here. It means that big adjustments are happening, right? That was the indication in October last year. And then intrusion and buildup. So when we see these kind of levels, then we know that we can have some other kind of changes that may or may not lead to eruptions there. We're not quite there. That would be all the way up here. We're down here at this level still in this really variable background. If I zoom into this area right in here, you can see also up and down, sometimes lower than a 400, sometimes higher, sometimes right at it. So this might, you could relate this kind of period to similar to what we're seeing now. And so that's the context, trying to figure out what it might be. So we might be building up. That would cause us to perhaps expect this possibility, not within days, but within weeks to months is the trend we see here. So we're still waiting for some sign of it being something sooner than that right now, and the outlook still weeks to months on Kīlauea for some renewal of surface activity. And of course, once we see these spike earthquakes, that'll be a pretty good indication that things are changing more quickly. So zooming in, looking at the past month here, we did have increased activity earlier this past week, right, with reaching up to 140 earthquakes in one day. Now we're earthquakes per day on this side over here. We'd had this is a little Pahala earthquake. I believe it was a 4.5 and a bunch of aftershocks, and this one's a summit event right here as well. So you can see the summit events are coming not constantly, right, but you see there's a pulse, and then there's another pulse right through there, and those are larger phases of adjustment in between the slower buildups to adjustment that we're seeing there. And so what does it look like on a map? Here it is, the past week on Kīlauea. And I will zoom in. So you can see pretty well here quite a lot of events in the summit region. Caldera is right through here. Right, you see quite a bit of dispersal actually northeast of the caldera underneath Volcano Village, in fact, all the way over here. Right, it's interesting that the adjustments are propagating perhaps into the rock that's not just right above the caldera, but around it on the sides, right? That's another indication of expanding adjustment, right? You see this area here, this is the Kauiki area right here. So you see that there are earthquakes activating through there, and it's interesting lineations. These lineations may or may not be true depending on how accurate these automatic locations are, right? Which just depends on data quality and all that. So right around a summit, perhaps a better chance of that, but so interesting lineations through there. And the bigger lineation is this Upper East Rift connector with all this activity in the past week over here, right? That leads perhaps to, this is Maunaloa right in there, so Maunaloa, Pauahi crater right in there might be the terminus of the main activity. Pauahi crater, which erupted most recently in 1979 and 1973 as well. So Upper East Rift is something that is part of the magma reservoir, and so it could pressurize and erupt anywhere within this caldera area or in this Upper East Rift connector is all fair game. When it does happen, if the patterns don't change by then, right? We do still see some activity over here on the Upper East Rift itself, all the way to Pu'o'o. Pu'o'o is right here. So this section right in here has some adjustment earthquakes within it as well. Definitely not as dense, not as many as up in here, but a little bit happening. And you still have a little bit south flank adjustment over here as well, which is expected because, all this stuff is adjusting, then all the land wants to push that way, right? From the side of the rift zone, push that way. And not surprising to see adjustments on the south flank there. And still mostly in this middle to Upper East Rift area by Pu'o'o, and some sparse, a little bit lower activity down further on in that right now. And so that is what we like to see. So that's the last week here, and it might look like a lot of earthquakes, and to compare it back to the end of 2020 and that buildup, I've saved that map for you guys as well. So wow, this looks like a lot here. I'm going to flip it to what it looked like in December 2020. And you can see that this was even more than we have now. See if we can line it up a little better there. And so similar kind of patterns, but definitely not as thick today And you actually can see little gaps between the circles here, and when it came down to building up to the 2020 eruption, you really didn't see any space between all this ink flooding all the earthquakes because of how many there are. All right, this was still a week or 2 weeks before the lava came out of the ground. All right, so another way to look at the earthquakes on Kīlauea is looking at the earthquake depths right here. And we have depth on this y-axis, and we have time now, this last week on the bottom here. So this blue stripe is the Deep Pahala earthquakes, and we want to know if they're influencing accounts that we're seeing. And we see there's a little bit of it's a little bit sporadic, but really nothing that's really like no huge event with a whole bunch of swarms following it that would skew our counts very much. So we can focus in on this upper band of the reds and oranges and a little bit of yellows as well. And what you might see is that about a week ago on the 9th, you can see there was a little flurry. Then you have a smaller flurry, a little bit of a gap, and then you really have, this is the period of heightened activity, really goes on from the 9th to the 11th right through there before it slows down quite a bit, right? And you can see that in comparison, the previous 3 days, while still showing some activity in that area, is not firing nearly as often. So still active, but variable rates over time, and it's not a constant pressure all the time kind of thing. So it's still building towards getting there. This is the 1 week view. Here's a past month view. So you can see a little bit more what I was talking about as far as the Deep Pahala earthquakes, because here you see more of clusters of Pahala earthquakes that could influence the counts, how they kind of cluster at times as well over the month, and that's natural. It's just that's part of the process, right? We're not sure exactly what are the pieces all involved down under the Pahala zone. But that's the same kind of process down there. And looking more at this upper zone like we just did for the week, you can see that there are times when you have less earthquakes and then times when you have more earthquakes. And looking at the more recent trend, you see there is that heightened activity, and here's a slightly lower activity, but still really it's still elevated beyond background levels for sure. Right, so this is really one of those flurries, and then this is just heightened activity, right? And perhaps something, there's not even something quiet enough to be background, but you see it's a little bit quieter in some periods, like right through here. All right, that's the past month. So the past month on a map has this layout. So now it looks a little bit more like we saw that plot for the couple of weeks before the 2020 eruption. The difference being we're looking at 4 weeks altogether there as opposed to just 1 week. So that's kind of the pattern you'd expect to see building up on a weak earthquake map. But this gives us a time average over the last month. You can really see the whole summit activating here, and really the Upper East Rift connector very easily visible. A little bit of the Southwest Rift, seismic Southwest Rift, showing right in here. I'll zoom in on that for you guys. There, a little bit of the seismic Southwest Rift, Upper East Rift connector. And you really see that this Upper East Rift area has had earthquakes, but it's been really not a whole lot compared to what you're seeing in Upper East Rift connector. Right? So if their lava is coming in here, it's coming in at a much slower trickle, apparently, based on the adjustment of the rocks than it is in this upper area right through here. Right? And remember, there's this bend in the rift zone right there as well, so that complicates things. South flank, you really see how it's been adjusting all the way up and down as a result of this intrusion of magma into this reservoir area right through there. All right, we'll wrap it up here with the deformation data. And looking first at the tilt. Tilt's still dominated by the deflation-inflation events. Looking at the past month here, like there's one big one, there's another one, lots of little ones in between, right? It's hard to really see the long-term trend. So, but maybe now we're seeing that if you maybe connect, maybe it was decreasing slightly or even, hard to tell, and then maybe it's been coming up. That's the easiest that you could tell from this particular tilt plot right in here, right? And so perhaps it's worth going to. There's another tilt station on the summit that's functional at this point in time. That's the Sandhill station over here, and you can see that it is either line, different slopes on either line, but there is this showing a more steady increase over the last month as well. So let's move back out. We can see that there, that steady increasing. So it's maybe less localized effects, right, at this station than we're seeing at the Wikihuna station, perhaps. So still, that's the pattern: inflation, long-term inflation, more easily visible on the tilt. Let's go back here to the deformation page. We look at the GPS across the Kīlauea summit, and it's more easy to see it there as well, too. It looks like now like an increasing trend. It looks actually like the same trend that we were on back in May, actually, right? It looks like it maybe sped up and then slowed down a little bit off of that trend here, but we seem to have resumed the previous trend and kind of caught back up to where we were before, which is an interesting thing, right? Perhaps leading further support to this idea of it being a localized effect that then averages out over the long term here. So, and that effect, of course, is something that was referenced last week in the USGS update and ours as well, of this shifting inflation center to the south of the caldera. And so that may be, well, what's going on with this signal right over here is it may have just sent a pulse that where the balance, the seesaw, think of it that way, was tipped more towards the south, and then it's realigned back to how it was before in the north, of the north showing the main filling center, perhaps, right? And so you've likely expanded your area to the south there, and you're still filling from below is the bottom line there, right? So that's the summit. At Pu'u'o, only minor changes. The scale is still very small over here on the side, and still very little wiggles as well. So not really worth dwelling on that any further there. So to attribute our source here, this is USGS weekly update for Kīlauea. It was issued this past Tuesday, July 13th. And similar information as we've been giving you, maybe not exactly the same words here, but seismicity slowly increased in recent weeks in the summit region. Continued summit inflation over the past several months. SO2 rates remain slightly elevated, and it's possible that it could resume eruption or that it's entering a longer period of quiescence prior to the eruption. The date we're still waiting for is a little bit over a month away, August 24th, when they'll actually declare it officially over, if no lava emerges to the surface by that point in time. So what's new in this update? They do report the 70 tons per day on July 6th. That was new. We just looked at a plot that had new information in that, so that's really nice to see. And otherwise, you really don't see anything new. You see the repeated statement once again that continued inflation was recorded by some GPS instrument. However, the pattern of tilt and GPS motions indicates that the inflation center may have shifted slightly to the southern part of the caldera. So they also say seismicity has been slowly increasing in recent weeks, though has not yet reached levels seen immediately prior to the December 2020 eruption. So that's all what we presented to you guys, and this is the source of the info here. No new information on the lava lake or the rift zone, really. Same thing, it does still state that it is refilling between the summit and Pu'u'o at similar rates over the past 2 years and before the 2020 eruption. So that is the text update. And that shift to the south, one last thing to say on Kīlauea about it is not surprising to see that, considering back, in the end of November and beginning of December 2020, a few weeks ahead of the eruption itself, we saw an intrusion, right? So here is the lead up to 2020, and this little green box is where the scientists they modeled where the magma had actually intruded from that central summit area towards the southern part of the summit caldera right here. And of course, we know that our other source is somewhere more in here, perhaps, and erupted more this way, right? So not surprising that we can actually activate some pathways to the south, as that was exactly the path that this magma took, it appears, in that build up to 2020, right? And this comes from the Volcano Watch article from December 17th, 2020, a small but notable magma intrusion at Kīlauea summit. This was 3 days ahead of the eruption of Kīlauea that happened that following weekend. All right, so let's just maybe try to recap it here and summarize it with a couple cross sections. Right, so there's the big picture. Let me go to this older image here, and not exactly what we have going on right now. Right, we do have magma going into the east rift over here. Right, we did have magma that popped up through one of these caldera faults, right? But we don't seem like we have two of them necessarily going up. And if we do, then maybe one of them is further to the south. I'm going to call this south and call this north, right? Because the rift zone starts off more to the south before it turns more to the east here. So that may actually work here for the east rift zone. So essentially you're having the bulge, right? Of this, whatever shape this magma body is, if it has one strand or if it has two strands or whatever it is, the bulge was coming up in the middle before. And then the bulge was coming up more towards the south, right? For whatever reason, whether it's a finger, it's injecting this way, which is not the pattern we saw, whether it's this whole thing bulging over in this direction, whether it's more movement from here to here and it collecting over here, that's not quite clear. All we have is to the south. And so we don't know what it looks like underground at all, but this is just to give you guys some idea of what might be shifting. It might be, you have a bigger knob there than you had before, or something like that, right? And so this is like essentially a localized change, at the surface, and back to this big picture cross section. That's all fitting in up in here, kind of like that, right? And so I can zoom in more. Our larger, deeper magma chamber, the South Caldera chamber, SC over here. It seems like its supply of magma in it seems to be pretty constant. This thing it seems like it's full and hasn't really wavered that much, right? So despite all of 2018, it seems like this has been the constant magma coming in from below into these upper areas. Right? So it's from here that the adjustment's happening to the side, to the south, but the constant is magma coming in. That's what's leading to all the earthquakes all above, all the earthquakes as it's coming in and pushing into this area, all the earthquakes all around here, right? So that's the situation now, is that we're pressurized seams, something like this. And that's our pressure. A little bit of the Southwest Rift too, right? A pressure zone, something like that. That's how our volcano is pressurized. I'm going to do that again in the yellow color here so you guys can maybe see it better. So Southwest Rift a little bit. That's all the pressure coming in here. And all the way down to that middle rift zone right through there. So some idea of what our reservoir might look like right in there. So last USGS photograph here, Kīlauea, surveying different points in the lava lake surface beyond just that one automatic point to try to get a better idea of how that whole surface might be settling in differential ways rather than just at one point. So that's interesting to see, and we'll look forward to their reports on their ongoing watch. So that is a Kīlauea segment here. So the last thing that we will do is the Maunaloa 1984 curiosities here. So let's turn to that here. And the title is Learning from the 1984 Eruption of Maunaloa. There's a couple maps that were put in the newspaper at the time over here as part of this article today. And so let me start off and use this article as the impetus for our curiosities here. And so let's maybe not read all the way through it, but I'll highlight the points of it, right? So let's start off talking about the earthquake activity. Inflation earthquake activity ramped up prior to the eruption so much that in June of '83, HVO indicated eruption could occur during the following year, though the timing was unknown. Next, they say increased earthquakes and tremor with a type of signal. Tremor that's associated with magma movement began mere hours before glow was observed at the summit of Maunaloa at 1:25 a.m. on March 25th, 1984. And it's from there that the flows migrated down to the side. So as our first curiosity, let's look at the earthquakes and a detection of glow on a volcano. Right. So this is a plot taken from that professional paper 1350, chapter 19, that we talked about last week, 1975 eruption. This is the 1984 portion of it. But now I'm going to point out some different parts of it, right? So this is a plot similar to ones we saw for Kīlauea. This is showing depth on the y-axis and time over here on the x-axis. And this is in years. 1984 is over here. 1975 is over here. So this is 1975 eruption with shallow activity and intermediate activity. So this is essentially the side of the magma chamber, and this is above the magma chamber. So you really see both going on here. So what you can tell is that there actually was quite a bit of intermediate activity that ramped up to the actual eruption right through here. So while the actual trigger for the eruption beginning, lava coming out of the ground, was only a few hours beforehand, there had been a pattern of buildup that lasted for years ahead of time, right? Really, you can see 1977, so maybe 7 years of it ahead of time there. And the shallow stuff came in maybe 3 or 4 years ahead of time as well, before the eruption came in as well. So interesting to note that the patterns, you can have these elevated activity, and you really can have short-term changes where it might seem like things are not really happening, and then suddenly it ramps up. That's the first curiosity to share with you guys there. And here's a different version of that plot that I've shown you guys before, really plotting shallow versus intermediate versus deep, with time over here on the side, and then now we have a number of earthquakes on the side here. So right, so you really see that prior to the 75 eruption, right through here, you had a ramp up of intermediate first, then shallow, then eruption. And similarly, in 1984, you had intermediate ramping up first, and then a shallow, and then eruption, right? With a notable 6.6 Kauai earthquake as a flank sequence there. And so, I think if I go down, I can get to, yeah, here we go. This is the cross section of where you see to the side here, these intermediate earthquakes, and above this zone of magma storage, right? Where you might imagine that shallower area of storage is somewhere in here, and that deeper area of storage that's more vertical, dike-like, is down in here. And so that's what we're looking at from the side there. And that's the earthquake pattern, as that kind of first curiosity of how that might look similar, or how it's really hard to tell, even if the long-term trends are really quite apparent. You can have short-term variations. And to show you that, I need to find here it is, the earthquakes in the month leading up to the 84 eruption, right, where we really see earthquake counts on the left here, and fairly low counts. And this is now all earthquakes without a threshold, whereas a previous plot we saw was magnitude 1.5 and above. So that's another curiosity we'll talk about here shortly as well. But you really can see that looking at all the earthquakes, even the really small ones, you didn't see a whole lot of buildup. And then you saw, okay, well, here's the buildup to eruption. Eruption begins right there. Then you have migration of the dike, of the magma underground, and you have another pulse of a lot of earthquakes as well. Then you have the eruption going on, and you see all of this is ongoing during eruption as well here. So looking at all the events may not be the cleanest way to look at this. If you look at with a threshold of 1.5 or 1.7 perhaps, you can more easily see these patterns, right? Everything's filtered out. We took out all that noise from these plots here, so you can see these patterns more easily. That's that curiosity of the earthquakes. So let me note one other thing here, and let me find it in this paper, or I bring it up. Okay, here it is. So it's discussed how the first glow was seen on that morning of the 25th at 1 in the morning, right? But it's been published here, and I'm going to make sure that we add this little curiosity as well, that 1 week ahead of time, on March 18th, a hiker spotted dull red glow along a crack on the Mokuaweoweo floor. That's Maunaloa Summit Caldera. Perhaps in 1975 fissures. This might be the crack that was glowing, but he didn't report that to HVO until after the eruption began, over a week later. So noted in hindsight, but there was glow a week ahead of time, right? Why is this important? Because in some future event, we now have thermal cameras up there pointing at the ground that can give that away without having to have a hiker walk back and tell somebody. All right, so then, actually 5 days later, 2 days before the eruption, or March 23rd, several observers spotted steam clouds rising above Mokuaweoweo. on March 24th, the day before the eruption, I'm not sure how you say this name, Godcho of Mount Holyoke College reportedly saw rocks and steam being ejected from 1975 fissures near the center of Mokuaweoveo, but there was no means to alert HVO. And this is still before cell phones, right? So, yeah, dull glow was spotted at 1 a.m. from further down in real time, but actually it was spotted up to a week ahead of time. There's a little curiosity there. And, you know, if you were watching this on thermal cameras, you would see first the glow, and then you'd notice, oh, look, there's steam coming out. And look, there's little explosions throwing rocks out of the ground. And all that would be obvious before the lava ever came out. And that's the advantage we have today in 2021. So, okay, let's jump back to this Volcano Watch and use it to give us some more interesting curiosities here. So they talk about how for the next 3 weeks, multiple flows advance slowly towards Hilo. They do note, this is a question we've had before, that much of the state was impacted by VOG, volcanic air pollution. So for those of you guys who are wondering about the gas coming out of the volcano, there was VOG coming out, and it was impacting the entire state, according to this HVO report here. And while we're talking about gas, and one thing that goes along with it is the weather. They do note that they monitor the eruption from ground and air, but adverse weather would sometimes prevent observations and therefore updates. This sentence is really interesting here. Heat release during eruption caused convective currents, resulting in local thunderstorms and snowfall in the vent region. So that would be pretty crazy to see, right? Imagine it snowing over the eruption from the convective currents and all of that, right? So similar to what we saw in 2018, but at high elevation, you might get snow instead of a dump of rain. Right, really fascinating there. Another curiosity of the weather there. And so let's go back to our paper and look a little bit more at what there is as far as the gas. And I will have to scroll to find the images here that I need. But yeah, here we go. This is one of the ones. So this is a view of the furthest down main vents of the 1984 eruption, around a 2,900 meter elevation. So this is just around a Red Hill area in a national park that's accessible. So the furthest, so we're looking from uphill to downhill, and the fissure begins right in here. It actually curves 20 degrees, and a little curiosity there, all the way to the arrow is the last downhill spot of where it actually is erupting, right? So that is it. Let me zoom in a little more, perhaps you can maybe get a better view. And so this Z-vent, as it was called, this is the furthest uphill, this fissure, and this is where most of the gas was coming out. And so they report reticulite and other more fountaining events occurring from right in here, and this is where you have this biggest pile of tephra, right, the cinder cone, as a result of that gas release. But the same fissure that was open, even with this zig in it, going downhill, down here at the bottom, there's a lava shield, which means the lava was coming out without shooting to the air at all. It was just bubbling out of the ground and bubbling over and building this low dome in that area. So out of this one crack, you have gas coming out of the uphill end right over here, and not nearly as much at the bottom here. So, imagine maybe there's like an upper layer of gas that this thing's tapping, and it all gets siphoned off uphill here. And not just here, there are other vents even further up the hill from the previous phase of fissuring that are releasing a whole lot of the gas as well. Yeah, and so we'll look at that here shortly as well. But that's an interesting part of the gas there, right? So the gas, we were imagining the gas coming up and forming these storms that could be happening a little bit over this vent, perhaps, but perhaps more likely further uphill at that image that I first showed you guys. That in this area right in here. This is the area that actually shut off of lava, but continued putting out quite a lot of gas for a long time. Okay, so let me go back to my 84, and I want to find you guys the cross section just down here. There it is. Let's get it further over. There we go. All right, so this is a cross section of that upper chamber, summit caldera, where magma came up at first, and then those fissures stopped and opened a fissure further downhill, and another one further downhill, and eventually all the way down at this 2,900 meters elevation. Right. So here's our cinder cone at the upper part, our lava shield at the lower part of it, right? And we actually had a whole bunch of gas coming out 500 meters higher elevation at this upper vent over here. And perhaps around there is another source of that heat and gas that could induce weather patterns. Right, so two sources. It's shown as bigger in this area here and smaller over here. So we'll be curious to find more details of that in the future and share them with you guys. And so that's, while we're over here on this panel, one other curiosity of this eruption is the migrating pattern of lava in the Northeast Rift. Right, so. The oldest eruption on Northeast Rift that we have mapped here is this 1855 steaming cone, and when it was pretty close to where E4 turned out to be. But it actually jumped back in 1935 to a more northern part of the rift zone. And ever since then, it's been steadily marching its way to the south. So 35 was there, 42 was there, 75 was there, and 84 was there. And why would this matter? This matters because this is a ridgeline right here, and if the next eruption comes out perhaps south of there, it would actually flow to the south instead of flowing north, and that'll come towards the area of Hawaii Volcanoes National Park in Kīlauea. And so that's just a future eventuality, not worth discussing further at this point in time, but this is a little curiosity of where the cracks actually opened up, and the pattern of the gas coming out of the ground on the northeast flank of Maunaloa here. So let's jump back to USGS Volcano Watch one more time here. All right. When we're talking about human impact and axis, here is interesting notes in this article here. The lava flows did not cross it. The Saddle Road, Highway 200 remained closed during the 1984 eruption. Spectators caused congestion in Hilo and some risked safety to trespass in the closed area. That is going to happen again every single time, probably, for the rest of mankind here, right? So, happened in 2020, happened in 2018, unless there's a viable viewing plan for people, right? Then people are going to be drawn to it in other ways that may be illegal there. So, something to think about in the future. Maybe you can set up a viewing area somewhere in the saddle, or a viewing area elsewhere. If you're worried about the saddle getting impacted by an eruption. As in before, the lava flow was going pretty close to the saddle road, so that would make sense there. Not right next to it, not right on it, but perhaps close enough to justify that. So they do note some power poles and lines were destroyed by lava flow, mainly impacted the NOAA Maunaloa Observatory and a relay station as well. They talk about civil defense response, and they talked about using a tiered system to evacuate. Condition 1, be on alert status, prepare to evacuate within 36 hours. Condition 2, flows anticipated within 24 hours, begin evacuating. Condition 3, you should be done evacuating and secure the area. Right, interesting how that might work and be updated in some modern fashion as we await the plans from the Hawaii Emergency Management Association that has been tasked by the State of Hawaii Congress to devise those Maunaloa emergency plans, evacuation plans here. They also note daily press briefings were held to share dynamics, locations, rates, hazards, and that's where these maps are an example of what readers in Hilo would have seen for this advanced rate, right? So eruption at Mokua Vale crater, fissure, southwest rift a little bit. Here's that flow that started going towards the national park before it broke open further down and started going down there towards Hilo there. And here's that furthest length of that first flow before it burst open and sent flow 1A before it did it again, and sent to flow 1B. And so in the end, it kind of ended up fanning out across this flatter ground rather than actually making it all the way into Hilo. Right, that's the pattern there, right? And so I think it's worth showing you guys the final eruption map of 84. Find it back up here again. There it is. So you can see there Mokuaweʻaweo at the summit, a little bit in the southwest, upper southwest rift area, and this is the initial upper northeast rift before Ulaula. Red Hill there is over here. So just uphill from there was that where that first spill towards the south, and then that fissure we were just looking at right up here with that vent Z and the lava shield was up in here. And you can see there is that long flow 1, flow 1A, flow 1B, and it was just fanning out without actually getting any closer to Hilo than that. Here's the edge of Hilo at the time, and you can imagine Hilo has probably grown bigger since then there. Right, so that's the flow maps. And they do, I won't read the rest of it, but they do note here at the end of this article that the technology is quite a lot different today, right? We now have webcams. We talked about that already, not just webcams, visual, but also thermal. They have a method of making quick maps, quick aerial photographs that are stitched together, thermal maps stitched together, DEMs with flow paths and steepest ascents, and we have all that other areas of impact from certain rift zone eruptions happening, produced by Truesdell, and all those impact maps, right, as well, and all that, and everything is online, and you have email and all that. So that's all the curiosities that we'll glean from this one little article on 84 eruption. Of course, 84 eruption to cover in full detail with all the images and media would take a much longer treatment than that. So I will just stop it at that for now, and we will wrap it up here, Dane, as you wish.
All right, I do want to thank a super chat that just came through. Our friend Gary Bryan, he says, "Thanks guys, great work. What I'm realizing is part of preparation for eruption is awareness and understanding of the history of eruptions." Definitely. 100%.
Exactly. That's exactly it.
One of the things we've started to do is on Hawaii Tracker, we just posted the first in a multi-part series looking at Maunaloa and some of the basics to know based upon the history that we're aware of. The history of Maunaloa, it's complicated, and just when you think you got a grasp of it, you start realizing, oh, well, the changes in technology completely, change what you're looking at. There's a lot of nuance there, but we're trying to give the basics of what residents need to really know if you're living on the slopes of the volcano or kind of one of these fall paths like in the Southwest Rift Zone, Ocean View, Kona Palisades, or on even Hilo side, because we've seen how 1,000 years ago eruption reached from HPP, Hawaii Paradise Park, all the way to Hilo Bayfront and span that whole area. So definitely worth knowing the history of them. Got a few questions here for you.
Yeah, there's long-term patterns, there's short-term patterns, and untangling them and having the resolution, that's really tricky, especially when you go further back in time and most of it's buried under the more recent, younger lava flows.
Right. All right, so let's get into some questions then. Robert asks about Kīlauea. There have been several quakes in recent days and weeks near the Puhi Ma'u thermal area. Is it possible this is an area of weakness?
So the Puhimau thermal area is an area that, how long ago has it been now? Gosh, it's probably been 85 or 90 years ago that magma intruded that area and started killing off all the trees in the area. So now all you see is grass, and the ground's too hot for ohia trees, for example, which are elsewhere nearby. So that magma's been sitting in the area for not quite 100 years, but a long time, close to 100 years underground, and it has not mobilized yet. It is an area of weakness in the sense where magma could move, and coming back to that pit crater discussion we had previously, if magma leaves that area, that could be the next pit crater where that could form. That could be a candidate for that kind of activity if that somehow can drain through some eruption in the future, right? The longer it sits there, maybe the less likely that becomes, because it's cooling, hardening, and all of that. But that's the kind of process that you'd look at. the Puhima area is interesting as well, because we've talked about how the caldera has several rings of faults, right? You have like your inner ring, and a little bit further out, and it's like a bullseye. And the farthest out series of fractures that I've often referred to as that Great Caldera area, that goes not too far from there. Yeah, not too far from that Puhima area. So it's really near that junction of that caldera edge and that Upper East Rift connector. So there's some other funny stuff going on there as well. So yes, it is an area of weakness. And anywhere from there down to Chena Critters Road all the way to Pauahi, given the current seismicity, would be fair game for something to happen. Yeah, have to pick up quite a bit for that to be the case, but that's what it's looking like right now.
All right, and if anybody wants to throw any more questions into the chat, I'll be going over them. We got one more here. Going to rephrase it a little bit. Bill asks about the impacts of solar minimums and other celestial events, let's say, that might have impact upon our volcanoes, either solar activity or gravitational effects or anything along those lines that you're aware of.
Well, so this is something that can be contentious to talk about, and it's part of it's because it's hard to come across hard data, right? But we do know this. We do know that when a volcano is primed for an eruption, which it reaches that state through its own internal processes, when it gets to that point, then really anything can set it off, right? It could be the tidal minimum. It could be the solar minimum. It could be some gravitational change. It could be an earthquake. It could be any number of things at that point in time, right? But first, the volcano needs to get to that point where it's primed and ready to go, and it needs its internal process to get there. Is the bottom line, right? So it's not like these things are causing volcanoes to erupt when they weren't going to erupt already. Because let's say that solar activity, for whatever reason, misses that one time. Well, if the volcano is ready to go, then the next tidal minimum might be what sets it off instead of the solar minimum. So whatever of the many candidates that are out there, whether it's some small Earth movement or something more exotic, we'll call it, that's definitely possible. But it's always a it's always a trigger for the whole bomb that's been primed by the volcano's own internal process.
All right. Well, I'm going to check one more time on these chats. I don't see any new questions here. So I do want to pitch that we're going to release another episode of Drones On immediately following this live stream, looking at May 31st and June 1st of the 2018 Kīlauea eruption in the Lower East Rift Zone, looking at the lava flow as it makes its way down to Kapoho from Fissure 8. So if you'd like to check that out, it's only 7 minutes long. We'll be premiering that shortly after this live stream concludes.
All right.
With that, back to you, Phil.
Mahalo, Dane. Mahalo, you guys who supported us. Mahalo to our regular contributors and you guys who asked questions. And once again, as Dane said earlier, please like, share, subscribe. That's the easiest way to help us spread our reach, and you can help without having to give us a single penny that way, right? So that's something that's we really appreciate. So mahalo, you guys. We'll be back with you guys next week, a week from today on Thursday once again, unless something unexpectedly requires our attention in the meantime. Otherwise, we will we'll once again keep an eye on Kīlauea and Maunaloa for you guys, and as usual, recap and discuss and keep on this educational process that includes learning about the history, not just of eruptions, but of movement of magma underground, of earthquake patterns, of GPS and tilt, and all those other things, all comprehensively painting a picture of what's going on underground. So that's our goal. Also, that really, when it comes into our communities again, we can be better prepared, more resilient, and we can jump into action more quickly, and more impactfully as well. So, mahalo.
Definitely.
Yeah. check out the drones on that we're gonna premiere here shortly. Anything else, Dane?
That'll do it for this one.
Yeah, he's Dane DuPont. I'm Philip Ong. Mahalo, you guys.